Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, now recall we have already defined what is the global dimension, right? It is supremum of all homological dimensions. So, now we will prove about global dimension. So, this is the theorem. So, AM local, Noetherian local always, and n is any integer, positive integer, and the following are equivalent. One, global dimension of the ring is less equal to n. And 2, tor j m comma n is 0 for all a modules m and n, and for all integers bigger equal to n plus 1. And 3, tor n plus 1 k is 0, where k is the residue field. So, you see this, only you have to check only one tor n plus 1, that is the advantage. All right. So, proof. See, the global dimension of A is by definition sup over all modules, the homological dimension of M. This was our definition. So, if, for example, if I want to prove 1 implies 2, we have given that this supremum is less equal to n. That means homological dimension of each module is less equal to n. But then earlier proposition we know, if I fix this module m and if the homological dimension of m is less equal to n, then for any module n and for any integer j bigger equal to n plus 1, tor is 0. So, that is what precisely this 2 is. So, this follows or immediate from 2 implies 3 of the, no, this is immediate from 1 implies 2 of the earlier proposition okay, that is 1 implies 2 and 2 implies 3 is trivial, because here it is j equal to n plus 1. So, take j equal to n plus 1 and the module m equal to module n equal to the residue field. So, the real proof is 3 implies 1. Okay. So, suppose 3 holds, that means I have given that tor n plus 1 k is 0, and from here I want to conclude homological dimension of every module is less equal to n, then the supremum will be less equal to n. So, enough to prove. So, assume, suppose that tor n plus 1 k is 0, and what do you want to prove? To prove homological dimension of M is less equal to n for every a module n M, finitely generated. All right. So, tor is 0. So, look at we want to prove that homological dimension. So, homological dimension of M is less equal to n, we know this from the earlier proposition. This is equivalent to saying tor n plus 1 m comma k is 0. This was earlier proposition, right? But we know that the tor commutes. I can interchange the variables because the tensor product is commutative. M tensor n is isomorphic to n tensor n. So, this is same as tor n plus 1 km, and this one is 0. So, earlier proposition says that third condition says if tor n plus 1 mk is 0, then homological dimension is less equal to n. But you see we have this, the other way. Anyway, this is 0. So, okay. So, therefore, it follows that homological dimension is less equal to n. So, this we have proved it for finitely generated modules. So, in the definition itself, one possibility is, in the definition itself we say that global dimension is by definition supremum of homological dimensions of M, where M is finitely generated module, and you can always reduce to finitely generated case, because one possibility is because the ring is Noetherian, and okay. So, this we will discuss this in a tutorial, how to reduce to the finitely generated case. So, here right now we are taking this supremum over finitely generated A module. So, because all our proofs will neatly work over work for finitely generated modules or Noetherian rings. Alright, so one corollary I want to note is, so one of the important corollary which one you are saying? Oh, this one. See, in earlier proposition we have proved that tor homological dimension is less equal to n, means equivalent to tor n plus 1 mk is 0. So, this is what we have proved. This we have proved. This if and only we have proved in proposition, earlier proposition, and this one is isomorphic to this. So, therefore, tor km is 0, tor n plus 1 km is 0. Now, we are proving what? We are proving 3 implies 1, right? We are proving 3 implies 1, right? Okay, so so 3 says tor kk is 0, right? And tor n plus 1 kk is 0, and the earlier proposition says you get the on a homological dimension of I apply the earlier proposition to so we want to prove homological dimension is less equal to n. So, therefore, enough to prove this is 0. Therefore, enough to prove this is 0. Okay. So, if you want to prove this is 0, earlier one, no, earlier proposition we proved homological dimension is less equal to n is equivalent to tor n plus 1 mk is 0 applied to k. Yes. Alright. So, corollary I wanted to note was, if you have a Noetherian local ring AM, then the global dimension of A is precisely the homological dimension of the residue field and the A module. So, we only have to check whether what is the homological dimension of A by M. That means we want to take a projective resolution of A by M and see how long the projective resolution goes. If the length is n, then the homological dimension is n. If the length is not finite, that means global dimension is not finite. This is very easy to check. Okay, now this is what. Now we want to give a homological characterization of. Is a homological characterization of regularity of regular local rings. Remember earlier we had two characterizations of regular local rings. One of them is the associated graded ring is a polynomial algebra, that is one. This is very important characterization because this says that the tangent cone is the affine space. And the second one was Jacobian criterion. This was, we have defined Jacobian matrix using the presentation of, and that we have proved it only for affine algebras. So we have taken affine algebra, then we have written a affine algebra as a quotient of a polynomial algebra, and then in terms of those equations we defined a matrix by using the derivation differentiation, and then we found a upper bound for the rank of this matrix, and when the upper bound is attained, that is precisely equivalent to saying the ring is regular at that point, at that localization. This was it. Now this one is more intrinsic, but of course the cost we are paying is the homological cost. I mean, so this doesn't, so the earlier two depended on the presentation, and one has to check that the if you write your affine algebra by different presentation, different maybe somebody takes a different polynomial algebra and then the equations will change and the matrix will change. So all this one has to check that they are equivalent, but if we do this way, it is intrinsic. Okay, so the theorem one wants to prove is AM local, then A is regular if and only if global dimension of A is finite. Or this is if and only if homological dimension of the residue field as a module is finite. That means A by M has a finite projective resolution. Okay, and after we prove this, then we will worry about what is this then, whether it is a crude dimension or not. Okay, so now so everything we want to do for the residue field, projective resolution, homological dimension and everything. So I am writing couple of lemmas for this. Preparing this theorem. So lemma 1, if I have, so our local ring is fixed. So suppose I have an element A in M minus M square. So this means this I can extend when I go mod M square, it is non-zero element in a vector space M by M square, A bar, this is non-zero here. So I can extend it to a basis, and a basis, when I pull it back, it will be a minimal set of generators for the maximal ideal, minimal number. So that means any such A, I can extend it to a minimal set of generators for the maximal ideal. See, this is not usually true for if your ring is not local, it is not true. You cannot extend to a minimal set of generators in general. Okay, so then, and we have a natural exact sequence from here. See M, see this M will contain the ideal generated by A. So we have this quotient, and from here M mod M times A to here there is a natural map. See, this ideal is bigger than this. So, there is a surjective map here, and what is the kernel? Kernel is this principal ideal mod this ideal M times A. So, this sequence is exact. This is exact, but I want to say more. This is a sequence of the sequence, short exact sequence of A modulo A ideals, A modules. All these guys are A by A modules, because all of them are annihilated by A. Alright, so this one splits. That means there is a map here in this direction, so that when I go like this, I get identity on this. That is the meaning of it splits. So, this such a map is called a section of this. Okay. So, I want to prove that splitness. So, proof. So, let us call this vector space M by M square, the dimension of this vector space, let us call it D. So, and as I said, A is not here means there exists A1 which is A, A2, AD in M such that their images in A1 bar etc. AD bar in M by M square is a basis, is A by M basis of M by M square. So, let us take A to be ideal generated by A to be the ideal generated by all these guys. Leave the first one. So, A2 to AD, this is the ideal generated by, is obviously contained in M, and M is generated by one more element. Alright. What do we want to check? We want to define a map actually. We want to define, what do you want to check? We want to say that this is a splitting. That means we want to define a map from this to this, so that this composition is identity. Okay. So, let us look at B. B in M such that B times A is in the ideal. Yes. So, what is this? See, M by M modulo ideal generated by A is like A2 to AD, because I have killed that A, and then I am trying to define a map. So, I want to analyze the situation when B is in M, so that B times A is in A, then what happens? Okay. First of all, let us look at A intersection A times A. I say this is clearly contained in A intersection M times A. One inclusion is obvious, A intersection M times A, this is clearly contained in A intersection A times A. This is ideal generated by A. Obviously, this is smaller ideal, so this is bigger ideal, so this is clear. So, this one we have proved it, because if you take B, so that, okay, so if you take any element here, if the multiple of A is in A, then B has to be in M. If you take any element here, it will be a multiple of A, that is call it BA. If it is in A, that B has to be in M, that is what we want to prove, but that is clear because of the minimality. So, this is clear, this is clear, therefore, what we got is they are equal. So, A intersection A times A, this is same as A intersection M times A. So, now you look at A plus M times A, mod M times A, this is isomorphic by usual standard isomorphism theorems, A mod A intersection M times A, but this is same as this. So, this is isomorphic to A mod A intersection A, but again get back, this is isomorphic to A plus A mod A, but this is same as M times M mod A. So, what we got? This isomorphic to M times A. So, which shows that means I have a map from M mod A to M mod, this is correct, M mod MA, M mod MA to M mod AA. I have a natural map which maps any coset here. So, let me, it is dangerous to write like that. So, so this one, this maps this one to isomorphically onto this. So, here you have this A plus MA mod MA. This should map, we have checked that this one is isomorphic to this one. So, these ones are isomorphic, these ones are isomorphic, this is same. So, I will map this isomorphically onto this. So, that will give me the section. This is the section. See, I wanted a map from here to here, here to here, but this one is isomorphic to this. So, I defined this way, this isomorphism will define this way and further inclusion, and that will give the splitting. Okay. So, now still we have couple of minutes, let us write one corollary. The corollary is again A Noetherian local and assume that the global dimension is finite, and let us take if A is an element in M minus M square, and I should also assume that A is a non-zero divisor in A. Then the global dimension modulo that small a is also finite. So, proof. Note that this the residue field of this new A by AA, that is this is also A by M. So, the residue fields are same, and to check that this global dimension is finite, I have to check that the homological dimension of the residue field as a module over A by A is finite. Okay. For that, so to do that I have to take the sequence of A by A modules and compute the TOR or whatever, right. So, look at, I have K here, K is the residue field, and then I have the elements here A by AA, this is the This is the residue field of this. And what is the kernel? Kernel is M modulo A. Now this is the exact sequence of A by A modules. And I am going to use this exact sequence to compute the homological dimension of this residue field. And if I check it is finite, then we are done. Alright. So, but you remember now, so global dimension of A by A, this is homological dimension as a modulo over A by A of the residue field. So, I have to compute this, but we have proved earlier that is okay. So, this one, so it is enough to prove that the homological dimension of this is finite, because this is a short exact sequence, and we have seen earlier how homological dimensions are related to this. I think this is one more than this. So, enough to prove that homological dimension of M by A as A by A module is finite. But we know now our assumption is global dimension of K is finite. So, that means homological dimension of as a module K is finite. This is precisely the global dimension of A, and if this is finite, that will also mean that homological dimension of M is finite as a module, because again use the short exact sequence 0 M A to K to 0. So, the homological dimension of this is finite, therefore, this will also be finite. So, this is finite, but now remember this A is a non-zerotive hazard. So, I can take a multiplication map on M, and then we have a short exact sequence. So, M A, this is injective, and the quotient is M by M A to 0. So, this is exact sequence. So, therefore, now this is A. This was MA is correct, image, no. So, this is MA is correct, and above lemma says that this is a direct summand of this. Splitting means we have proved the above lemma that says that M by AA is a direct summand of M by MA. And this one has a homological dimension finite, therefore, this one will have homological dimension finite. So, direct summand of this is homological dimension finite, so direct summand will also finite. So, this will mean the direct homological dimension of this, because this is finite by this exact sequence, this exact sequential, this is finite, therefore, this homological dimension will be finite, and but this one is a direct summand of this one by the earlier lemma, therefore, this one will also have finite homological dimension, and that finishes the proof. So, and we will continue this. We have not yet finished we just started the homological characterization. So, that I think we should be able to finish next time, and then we will spend some time on the fact that regular local rings are UFDs.